This meeting is being recorded.
In this video, we'll review section 7.9 and we'll review the process, specifically how to predict which products we would be given a certain substrate and reagent. So we've seen a number of factors affect which products will be formed when we react alkyl halides with either a nucleophile or a base. So again, we would call these either the substrate is our alkyl halide, the reagent slash solvent can be our nucleophile or our base. So we can see also that a mixture of substitution and elimination products can be obtained. So in this example shown here, we have our alkyl bromide. We react with a strong base, so we see both elimination, E2 products, and SN2, a single SN2 product. And we'll look at all the considerations that need to be made, such as inversion of configuration when we have a chiral center. So if we have a single product, we can build upon this and see how we can determine when there's going to be multiple products. So let's look at this substrate here. And we have to consider how we would go from this alkyl halide into our desired product. So we see that we have this sodium methoxide here. So this will produce an elimination product. So first, in our analysis or our plan, we should always follow this three-step analysis here. So we want to determine the function of our reagent. So is it functioning as a nucleophile or a base or both? Then we want to, in step 2, analyze our substrate. And from that cross-section between the function of the reagent and the substrate is either, for example, primary, secondary, tertiary, benzoic, allylic, any of these. We can then predict our expected mechanism. And then last, we would consider any relevant radiochemical or stereochemical requirements. So let's take a look at what that would look like here. So in step 1, again, we're going to look at the function of our reagent. And we know that with SN2 reactions, we require a strong nucleophile. And then with E2 reactions, we require a strong base. Whereas with SN1, we can utilize a weak nucleophile, and E1, similarly, a weak base can be utilized. So down below this table here, we have some different categories where in this first column, for example, we see compounds or chemicals that can be used as strong base, weak nucleophile reagents. So we have these compounds DBN, DBU, and sodium hydride listed here. So these will only promote the mechanism of elimination, specifically E2. Then in our second column here, we have SN2 and E2 will be competing reactions when we have a strong base, strong nucleophile. So both nucleophilic substitution can occur, but also elimination with hydroxide, methoxide, or ethoxide. Then we have SN1 and SN2 reactions, which can occur with weak base, strong nucleophile. So both SN1 and SN2 can have these nucleophilic substitutions. And then last but not least, in our weak base, weak nucleophile category, we see things like water, methanol, ethanol, and these would facilitate SN1 and E1 mechanisms. So in step 2 now, we're going to analyze our substrate. So that's what we see listed over here. Do we have primary, secondary, or tertiary substrates? Depending on which, we can see which mechanisms will dominate. So we know if we have a strong base, weak nucleophile, we will always have an E2 elimination mechanism. So that you really can just memorize or just always know that strong base, weak nucleophile, only elimination, specifically E2, will occur. And then in our second column, with primary substrates, for example, we'll look down this row here, elimination occurs less likely. So that would be our minor products there, and then our major products we would see with substitution here. So this happens, we can see according to this square, a larger percentage of time compared to E2. And again, this is with strong base, strong nucleophile. So we have those competing reactions, except with a tertiary substrate where, again, only E2 mechanisms will be seen. And then we kind of shift over here to weak base, strong nucleophile, where everything primary and secondary will be SN2, and then we have solely SN1 mechanisms seen with tertiary substrates. Again, these are the strong nucleophile, and the compound cannot function really as a base, so there's no competition. Last, we have the weak base, weak nucleophile, which only reacts with tertiary compounds or those that are stable like alylic and benzoic. So we would see SN1 and E1, again, with mixed products. So we also need to consider the radioselectivity and stereoselectivity, and this happens in step 3. So after we look at our reagent and substrate and we decide what mechanism we'll have, we have to draw all the possible radio isomers and stereoisomers, and then determine the major using the guidelines that we've looked at. So some to review are that when we have an SN2, we should observe a single product, which would be an inversion of configuration at our alpha carbon. And also, when our SN2 reaction happens, the nucleophile will attack this alpha position where that leaving group is connected. And that's how this inversion of configuration happens. So again, for step 3, say we have an E2 mechanism, we would draw all possible alkene isomers, and only alkenes that result from a beta hydrogen that's anti-periplanar to our leaving group can form. So we can eliminate products that would not form using this rule. If we have a bulky base, the Hoffman product is our major product. But if we have a non-bulky base, then we go just based off the most stable alkene as our major product. So again, generally the Zaitsev product is favored in E2, and then the Hoffman would be favored with a sterically hindered base. So Zaitsev, unless that sterically hindered base is used. For SN1 mechanisms in our step 3, analysis here, we know that our nucleophilic attack of this carbocation will result in a mixture of configuration. R and S products will both be formed, so we have to draw them both. And the reasoning behind this is because our nucleophile replaces the leaving group and gives this nearly racemic mixture. So remember, there is always that slight inversion over retention. And then last, we have E1 mechanisms. We draw our carbocation that's formed after the loss of leaving group. And then we know that our possible alkene isomers will result from elimination of a beta hydrogen. So we know that all of these possible stereoisomers will form if it is not, or because E1 reactions are not stereospecific. So we generally can say that the Zaitsev product will be favored over the Hoffman. And when applicable, if both a trans and a cis isomer, the trans disubstituted would be favored over a cis. So how can we predict products, again, we look at our reagent. So in this case, we have sodium hydroxide. It's a strong base and a strong nucleophile. So both of these, SN2 and E2, will be favored reactions. Now we look at our substrate. So that's this guy right here, our alkyl halide. This would be a secondary alkyl halide. This is our alpha carbon here. This is our leaving group. So both SN2 and E2 can occur, but we know that looking at a previous image, rather, here it is here, that we would have domination of one reaction over another with a secondary substrate, right? So E2 is going to dominate over our SN2. So let's go back and let's look at what products we can predict. So again, we have our SN2 product first, and we know that backside attack will give us the inversion of configuration. So we see here inversion of our methyl group and our alcohol SN2 product. Then we have here with our E2 elimination reaction, we have to consider both the regio and stereochemical requirements. So here, if we eliminate our hydrogen A, we would see our trans product form. If we eliminated hydrogen B, the cis alkene would form. These would both be our Zaitsev products. But then we have our elimination of any of these equivalent hydrogens here, hydrogen C, we will get this Hoffman product. So again, the regio isomers are all drawn. Now let's look at our stereochemical requirements. And again, we know that we have this inversion that happens here. Our major product would be, again, that E2 pathway being the major pathway. We would choose our Zaitsev product that is trans orientation, if possible, as our most stable product. So we'll take a look next time at section 7.10.